How's it going, everybody? Today we're going to talk about kinetics 5.3 concentrations and its changes over time, both integrated rate laws and half-life of reactions. Alright, so in the previous lesson we talked about rate laws, how they're super important because changes in reactions generally can be measured using changes in concentration over time. However, when we're talking about zero order integrated law, we're talking about the exact same thing. But now we're going to be using calculus to produce a separate one. We're actually going to be measuring it in terms of time. So if you think of calculus as an example, there's differential equations and integrals. And in calculus, you basically are going to talk about how I can integrate this rate law in terms of time. So if we rearrange this equation, you're going to get concentration of time minus concentration of A, concentration of A of t, and concentration of A at 0 or initial equals to negative kT, where 0 or naught is the initial concentration at 0 seconds and t is after a certain period of time. So here we're really talking about rate in terms of time, but if I want to take a look at the change in a specific period of time, I can go ahead and do an integration with that. So let's go ahead and dive into rearranging this equation. If I rearrange this equation for a zeroth order integrated law, you rearrange it to get AT equals negative KT plus A naught, and that actually gives you a Y equals MX plus B. So it's a pretty straightforward one if you kind of go back to this idea of putting in as a K is equal to A naught here. And so the plot of AT versus T, or the time, produces a zero line for a zero order reaction. And this is used to determine if the reaction is a zero order or the straight line will occur if the reaction is a zeroth order. So when you're using these types of integrated rate laws, what you're really trying to figure out is what is the order of that reaction relative to time. Now, if you don't have time, you have concentration, you obviously have to deal with the other one. So if you have a straight line and relative to A, time, then what you're going to end up getting is a zero order. And here is a graph of a zero order reaction for CH3CH2OH yielding hydrogen gas. And so if you plot this over time, and you're going to take your concentration over your time, and if you get a straight relationship or a negative K relationship, you're probably going to end up getting a zero order. So graphing is a huge part of these ordered reactions when you're talking about that. I usually just like to memorize this idea. Downward sloping lines are going to give you, when you're doing concentration versus time, of specifically these integrated laws. Now, zero order reaction is, let's take a look at a problem where we have here. So using data provided, find the rate law and the rate constant of delta T over time. And here they're telling you that time is at 45 seconds, concentration is dropping from 1.50 to 0.9. And so the first question is, we need to find the rate law. So we already know it's a zeroth order rate law because the plot of AT versus T gives a straight line. So you can see from here, this gives us a rate constant and a rate law. And A yields B plus B tells us that the A is the only reactant, so that makes life a lot easier. So once we do that, we plug in the rate law, so the rate equals to K. So that's a pretty easy way of doing it. Now to find K, we're going to plug in 0 to T450, so we're going to use negative KT equals to AT minus A naught, our initial, and then you're going to subtract it, which gives us our K value. So whenever you're using these integrated rate laws, you basically have to use the A0 equals KT values, and that's going to give us K 1.33 times 10 to the negative 2. So this is more of a plug and chug for a zero order. Now, let's talk about a first order integrated rate law, and this is going to be a little different because we already know that in a first order integrated rate law, you can also deal it with in terms of a calculus, but here now we're going to be using the ln function, right? So we're talking about not having that A in there. To integrate this, we're going to use the ln of A minus ln of A equals negative KT, where 0 is the second point. We rearrange the equation to give ln of A T equals negative KT plus ln of A initial, and the plot of this one gives us a straight order reaction for a first order. So again, if you're plotting ln graphs and you get a straight line, then you're definitely going to get that first order. And so here is again the same thing. It's going to be a negative slope or negative k. Your y-intercept is going to be the ln of a0, and over time, as you guys can see, we're going to end up getting that first order. Okay. All right, so here's an example of a first order reaction using data to provide the following: the rate law, the rate constant, a at time equals 5.0, and then let's go ahead and run with it. So as you can see from here, ln of at, we're going to go ahead and take a look at the data. So we know it's a first order because a plot of ln a versus t gives us a straight line. A yields b plus d2 tells us that a is the only reactant, so the rate law equals rate equals ka. So when we're talking about integrated rate laws, we're really talking about looking at graphs. Really, that's what it comes down to. I mean, it's pretty straightforward, I know, relative to the differential ones, but it makes life a lot easier. All right, to find k, we're going to basically do the exact same thing. We're going to take the ln values, ln of 0.017 minus ln of 0.020. We pick at 0 and any other time. Your k is going to be the same, so 3.3 times 10 to the negative 3, and we're taking a look at that. Now to find a at 500 seconds, we're going to use data at t equals 0, and we're going to take the ln values. And so if we want to find out what the a value is at a specific point in time, since we already know the concentration of a, and we already know what t is, we want to know and we already know what k is in t, we basically have to do the ln of a equals to that. If you take a look at that, you're going to have to get rid of the ln function and then use e to crank out your actual value. So at that specific concentration, it's going to be 3.8 times 10 to the negative 3 molar. All right, first order reaction. Here's another example. So it says here, data from an experiment which examined the change in concentration over time for a first order process 25 was used to plot the graph below. Sketch a line that shows the approximate results that would be expected if the same experiment was repeated at a lower temperature. All right, so first step, you want to understand that obviously we have a straight line here. This obviously is our first order. We have ln of b, we have one reactant, and over time it definitely goes in there. So what they're asking us is to sketch a line if we lower that at a lower temperature. And so the idea here is that the rate is slower, so AB is going to decrease less rapidly. So if you take a look at the line graph, the slope is going to be at the speed at which you're actually getting that. It's going to be that k value. But because it's slower, it's colder, you're going to get a flatter line. So you can kind of sketch this a little bit. It doesn't have to be exact here because I'm not giving you any values. But obviously we already know from collisions that colder environments generally have lower reaction rates. All right, that brings us to our half-life for first order reactions. And half-life, as you guys already know, is the time it takes for a concentration of a reactant to decrease by half. So, we usually use this for radioactive dating to determine how old things are. So we take every half point, that's half of what's already been used up. So A0 at t half time for here, let's assume this is the half-life. We've already divided by 2. We take the second one, and we increase this to another half-life that's already divided by 4 and divided by 8. So half-lives are going to be first orders. So what we're going to do here is use a first order reaction and to find the half-life of this. And so here's our equation, here's our line. We know it's N2O5. You have one reactant, which makes life a lot easier. We already know that this is going to be about negative 493. So what we do is we first need to find K. All right, so to find K, we're going to have to use the ln functions again, or find the slope. Since we already have the equation already, all we need to do is find the slope of that. And we find that the slope is 1.70 times 10 to the negative 3. Once we find that, we already know K, and so K is going to be negative 3 seconds minus. To find the half-life, we're going to stick in that K value into our ln function to find what T is, right? And so T is going to tell us, based off of that, based off the concentration from ln of initial of ln 0 to ln 0.5, which is our time that we're trying to find, the concentration 0.5, we fire out that this is going to be 408 seconds. Now, again, taking a look at these values here for the concentrations, you can kind of see it right here. If you're taking a look at your ln value of, negative 4.93 and 3.91, which is your slope, And then here you're taking a look at your ln of 5, which is your concentration, right? So your concentration will tell you, and it's kind of a little difficult to change that, what your initial concentration is for each value. So here is where you're actually getting that ln value, okay? All right, so once you do that, you're going to get 408. And so 408 is going to be what you're interested in. And the half-life is inversely proportional to the rate k. And if k is small, the reaction is going to be slow. So every 4 and 8 seconds, you're going to get that half-life. Now, deriving the half-life equation, you're going to take the half-life by dividing the ln of 0.5 minus the ln of 1. And you're going to get that 0.093, and then you're going to get that k value, which you already have. All right. And so now, when you get that point, remember that the 1 and the 0.5 represent the half-life. So you want to set your initial to your final at 0.5 to derive those, and then at that point you can figure out what that half-life is. And they're always going to be first order. All right, so here's the half-life equation. Again, taking a look at first orders. Which of the following process has a shorter half-life? Justify your answer. So process 1 has a k value of 428, and process 2 has 296. And so the first one would be process 1 has a shorter half-life, and the reason why is because it occurs at a faster rate when both systems share the same initial concentrations, as this rate constant has a larger magnitude. So the larger this magnitude is, the faster it's going to get consumed, which means that you're going to get a shorter half-life. All right, so looking at second order integrated rate laws, going out again based off that idea and using that equation, we can see that rate equals negative delta A over delta T equals K delta A, A squared. We use the calculus now to derive this equation. It's going to be 1 over AT equals minus 1 over A0 equals KT, where it's the initial point. So again, very similar to the ln function as we saw last time. And we can rearrange this to find your y equals mx plus b. And so if you plot 1 over A versus time, you're going to get a second order reaction. And basically, if you crank this out, you're going to start seeing a positive slope. So again, in a second order reaction, you're going to get a positive slope on a 1 over A concentration versus time. And so your slope is going to be k as usual, and your intercept is going to be 1 over A naught. All right, so here is our example, and the question here is find the rate law and the rate constant for these. Now, usually they'll give you 2 graphs or 3 graphs, and they want to figure out what that is. And so based off the curve that we see here, this is actually a curve for the ln function. So we already know, obviously this is second order because it's a linear function. And so we know it's a second order because it gives us a straight line. And so for this, they tell us that NO2 is the only one, so we know that the rate is going to rate equals K NO2 2. Now to find that, we need to take a look at the data, and KT equals 1 over AT minus 1 over A naught. We plug these values in, and then we're going to solve for K. So again, you're picking some of your final, your initials, and for any other time, going back to the graph, and you're going to be able to solve for that. Okay, so here's another example. So we're taking a look at this experiment where we're changing concentration over time for a second process, and we're using to plot that graph below, sketch a line that shows. So again, we're trying to find if it's at a higher temperature now, so obviously we expect this to have a steeper slope, and so the faster this one is, it's going to be a faster decrease over time. Alright guys, well hopefully you enjoy this. This is going to be all over kinetics. We'll do some practice problems. Make sure you take some notes. See you guys later.